Hi students, and welcome to today's discussion on the quantum model of the atom and the quantum numbers that tell us where electrons are in the atom. I want to start today by talking about Schrodinger's cat. You may have heard of this concept before, but I'll summarize, probably simplistically summarize for the quantum physicists in case you listen to this. But in paradox of Schrodinger's cat, there is a cat in a box, and that cat could be alive or dead. They've created a mechanism at any point the box could kill the cat. So the cat is either alive or dead in the box. The only way to know whether or not the cat is alive or dead is to look at it. And at that point, you no longer are wondering where it is. You kind of change the scenario because you have observed it. This concept of we don't know where it is until we find it, but once you've found it, then it's not lost traveling anymore. This kind of paradox in our mind is sort of where the quantum mechanical model or this idea of entanglement kind of comes from. And this quantum physics, this quantum world becomes very philosophical and something that you can really debate about for a long period of time, and people will find very entrenched beliefs in this kind of a system, but the reality is that we don't know. And once we do know, all of our conversations will be moot, which is kind of the point of Schrodinger's box. So we are talking about the quantum model of the atom. And as we mentioned in the last video, if you picture a windmill with its individual blades, as the electrons start moving in the atom, they're moving so fast that we start to get this whirl. Instead of a nice Bohr's model of the atom, the position of the electron begins to look something a little bit like this, where it could be in many different places in three-dimensional space at any time, or it could not be there. We gave the example of you being in your homes, watching this video. Your parents say they're in their room, but when they go to look for you, maybe you've gone to the bathroom, or maybe you've gone outside for a walk, or maybe you've gone to get a snack. And for that moment, you're not where they expected, which does not mean that they were wrong or that you were wrong. It just means that sometimes things don't follow the pattern that we expected them to follow. All of this kind of uncertainty gives rise to the quantum model of the atom. And we see this quantum model starting from the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle states that it is impossible to determine simultaneously, that means at the same time, the position and velocity of an electron or any other particle. The position is its location. The velocity is where it's going. So the idea is, if you had a picture of a football and the football was flying through the air and you snapped a still photo, you could calculate its position, but you could not tell me where the football was going. Had it been dropped straight down? Was it going across the vision? Was it flying sideways? You don't know. From a still photo, we're not sure where it's going. So when we stop an electron enough to pinpoint its location, we don't know where it's going to go next. And if instead we're watching the football travel, then we know where it's going, its velocity, its speed and direction, but it's too hard to say where it is because it's moving. Every time we've measured where it is, it's moved. So this is the Heisenberg uncertainty principle, and basically what it tells us is that we cannot know both where a particle is and where that particle is going, because when you stop it to observe where it is, or when you calculate to know where it's going, it has moved. The particle has changed. So this Heisenberg uncertainty principle is really explaining to us that you can never know where an electron is in an atom. We're kind of back to this picture of our quantum mechanical model of the atom with the electrons moving all around. But now that we know, based on the Heisenberg uncertainty principle, that there's no way to know where the electron is, we are going to spend the remainder of our time in this chapter pinpointing where the electron is, which I know seems like a little bit of an oxymoron, but it's like we were to go back to the case of you in your home, and I were to say, well, you know, you can never know for sure exactly where your child is at every moment of the day because they may take a left turn, or they may go to the bathroom, or they may go get a snack. And so your response to that is, well, then fine, I'm just never going to care where they are. They can just go wherever they want. I don't have any rules for them anymore. Well, that's not exactly the response, right? The response is, well, yeah, but I can know where they are most of the time. I can have a good idea of where they're going. I can know where I expect them to be. And that's really what we're doing with this quantum model and with what we're going to be forming into orbital diagrams and electron configurations and quantum numbers. So let's get started. We're starting by looking at the 4 quantum numbers of the atom. So every electron in the atom, and you know that we can have lots and lots of electrons in the atom. Lead has 82 electrons in it. And so if lead has 82 electrons, imagine like they were 82 kids, lead needs to know the difference between each electron. And so each electron is given a set of quantum numbers, and no 2 electrons in the same atom will have the same set of 4. So each electron has their own specific determining set of numbers. Very similar to like a social security number or even an address, right? If we were to think about our address, you can say, well, where do you live? Well, I live in Torrance. Okay, great. You live in Torrance. But could you narrow it down a little bit? Oh yeah, okay, I live on Torrance Boulevard. Okay, great. Well, Torrance Boulevard is still kind of really large. Okay, well, I live at 5430 Torrance Boulevard. Okay, well, that's getting closer. Okay, I could find you now. But if you showed up at 5430 Torrance Boulevard, you'd find Bishop. Okay, well, now you need something else. I live in room 103. I don't really live there. I live in room 103 at 5430 Torrance Boulevard in Torrance, in California. Now you know where to find me. Okay, that's what our quantum numbers are really telling us. So we're going to talk about the 4 different kinds of quantum numbers, and this is a really important line of demarcation. I hope you're listening. You do not need to know the 4 quantum numbers by name. It's just hard to talk about them if we don't name them. So we're going to eventually just start using the quantum numbers to do electron configurations, and that's how I'm going to assess your knowledge on this information. I'm not going to say, what are the different magnetic quantum numbers that can exist in the p orbital of principal energy level 2? I'm not going to ask you a question like that. What I am going to ask you is, can you do this electron configuration? And knowing the quantum numbers is how you learn how to do the configuration. So bear with me through this part. We're going to go through our set of 4 quantum numbers, and then starting in our next video, we're going to put them into practice, and we're going to start using them and feel a little bit more comfortable with what they do. So the 4 quantum numbers tell us 4 different things. The principal quantum number tells us the size and the energy level, the distance from the nucleus that the electron is. So electrons that are close to the nucleus will have a low principal energy level, and electrons that are far from the nucleus will have a bigger principal energy level. The angular momentum quantum number is going to tell us what overall shape does the orbital look like. Is it a sphere? Is it a figure-8 shape? Is it a 4-leaf clover? Is it something way more complicated than that? What's the overall shape of the path of the orbital that the electron is in? The 3rd quantum number is the magnetic quantum number, and this one tells us in what orientation in 3-dimensional space is our electron traveling. And so the magnetic quantum number is going to tell you, is it in the X, the Y, or the Z axis? Okay, because this is a 3-dimensional atom. And then lastly, the spin quantum number is going to tell you in which direction is the electron moving. Is it going forward or backward around the orbital? So each of these quantum numbers, we're going to take them again one at a time, but each of these quantum numbers tell you a little bit more about the electron. Is it close to the nucleus? In what shape is it traveling? In what space is it traveling? And then in what direction is it traveling? So those are the ways that the 4 quantum numbers tell us about where the electron is located within the atom. Our first quantum number that we're going to look at is the principal quantum number, or the principal energy level. And this is referred to as N. The principal quantum number, or the principal energy level, tells us how far away from the nucleus are we. So in this picture, you can see that energy level 1 is the closest. The nucleus would be down here. And then 2, 3, 4, 5, 6, they move up, up, and away from the nucleus in the center. So N is going to be a whole number, something like 1, 2, 3, or 4, and they go up as you move farther and farther away. So this gives the electron an infinite number of distances from the atom. So the principal energy level on its own tells us how far away from the nucleus the electron is, but we don't want to just keep moving out like N equals 1, 2, 3, 4, 5. We'd have to get our numbers up way too high. So what we do instead, or what we find, is that the electron could be in different shaped sublevels beneath the energy level. So if they're in energy level 1, they're going to have one sublevel. If they're in energy level 2, they're going to have 2 sublevels. Energy level 3 has 3 sublevels, and so on and so forth, until we get up to, N equals nth sublevels. And you can see that there are some letters here that are indicating what kind of sublevels they have. So principal energy level 1 has 1 sublevel, and it says S only. Principal energy level 2 has 2 sublevels, S and P. So each of these sublevels has its own shape and its own letter that indicates its shape. So we're going to go through each of the sublevels and get an idea about the letter corresponds to a shape of the orbital. Our first sublevel in every orbital is S. So every time we come back around to a new principal energy level, we're going to come back around to an S orbital. And the S orbital shape is a sphere. Okay, so a sphere is a 3-dimensional, any ball will do, a soccer ball, volleyball, basketball, baseball, it doesn't matter, not a football. They're all different spherical shapes, and so there's only one possible orientation when we talk about on what plane is it on. So remember, we're going to look back at our other quantum numbers for a second. So our angular momentum quantum number has a letter, I know that's weird, but it has a letter that tells us what that particular orbital looks like. So we have S, P, D, F, G, and H. Those are the different letters that correspond to the angular momentum quantum numbers. And S is a sphere, spherical in shape. And there is only one possible orientation. So my magnetic quantum number is what I'm listing here beneath it. So this here is my magnetic quantum number, where this is my angular momentum quantum number. And those ones really go together. They'll blend together in your mind. It'll be hard to separate them eventually. And we don't make a big deal about separating them. But my S orbital has only one possible orientation because my S orbital is just a sphere. The p orbital has 3 possible orientations. So my p orbital is a figure 8 shape, and there are 3 possible orientations for my p orbital. Now, it's important to remember that a figure 8 feels like a planar shape, but our p orbital is actually more like an hourglass. So we're going to look at what that looks like. I have some balloons here, and I know it's hard for them to even fit in the screen, but I have some balloons here, and this is kind of what it looks like to have a p orbital. So if my hand holding them here is the nucleus, the p orbital is going to be anywhere along the surface of the balloon. So this is allowing the electron, it could be anywhere on the surface of either the green or yellow balloon. And we say there are 3 possible orientations. You can see that pretty clearly like this. I can be along the x-axis, I could be along the y-axis, or I could be along the z-axis. So my figure 8 shaped balloons could be traveling their orientation. There are 3 possible orientations that they could exist in. So we say that our p orbital, which is just the figure 8 shaped orbital, could be in any of 3 possible orientations: towards you, across from you, or up and down. And that gives us the 3 possible orientations for our p orbital. The third level is the d sublevel, and the d orbital is in like a four-leaf clover shape. So we've got our four-leaf clover shape for d, and it has 5 possible orientations. The 5 possible orientations for D put the orbitals, you can look at them here, either between the axes or along the axes. And even this one in the middle has them both really along the z-axis, with the second one kind of circling the first. So I just want to take 1 second. This is the last one I'm going to show you. We're going to look at the d orbitals with balloons. So this is what a d orbital might look like in balloons. It's going to have 4 different places. So this is just one single d orbital. And imagine the electron could be anywhere along the surface of any of these balloons. So when we say that there are different orientations, we could have the orbital look like this, or we could turn it this way. We could be coming at an angle to you. These orbitals could be in any possible direction. And if we tried to make them both go up and down, like in the z-axis, you imagine these, the red and the blue one, might start kind of spinning around the system, and that would make them look like a little world, just like the windmill that we talked about before. And so it creates this almost like a tunnel, like another shape of an orbital that's there. So the d orbital, we say it's a 4-leaf clover shape, looks something like that, okay, with all of its 5 possible different orientations. It's maybe not a stretch of the imagination to feel like the F, G, and H orbitals are going to be getting even more complicated. So we say for all of these that their orbital shapes are indescribable. And basically what that means is that they're too variant for our brains to put down computationally into a picture. The 4th level, though, is assigned a sublevel of F, and it has 7 possible orientations. The G sublevel has 9 possible orientations, and the H sublevel has 11 possible orientations. And so if you're real savvy, you may have figured out that for our magnetic quantum numbers, how many orbitals they have. For our magnetic quantum number, or how many orbitals they have, we are doing odd numbers here. So F, G, and H, I'm going to put just little question marks for their shapes, because I don't want to leave out, like you would look back and think maybe you only had part of a chart done. So our principal quantum number, as we move away from the nucleus, we have our principal energy level. Then we know what shape the electron is in. We know what orientation in 3-dimensional space the electron is in. And finally, we're going to talk about, well, which direction is the electron going? So for our 4th and final quantum number, we have the spin quantum number. And for the spin quantum number, we are looking at what direction does the electron move. So we are able to put 2 electrons in a single orbital. So each orbital, this is my s orbital, remember, each orbital has 2 electrons in it. However, those electrons cannot be traveling together. They have to be traveling apart, because electrons are both negative. They don't want to be in the same space. They want to be stretching out and getting as much space as they can within the orbital. So if one electron is on this side, then the other electron wants to be on this side. And they're going to not travel towards each other, but they're going to travel kind of in opposite directions, spinning around the electron. So we say that one travels clockwise and the other travels anti or counterclockwise. And I just want to show you the right hand rule. So everyone, take your right hand and put it out like you're going to shake my hand. Okay, we're going to shake hands through the computer right now. And what I want you to do then is to bend your fingers so that they go counterclockwise. And so if you're looking at a clock, okay, so if it goes 12, 1, 2, so if I want to bend counterclockwise, I'm going to be able to spin my hand this way, and I'm going to end up with my thumb pointing up. So we would call that a spin up or a north up spin. If I wanted to bend my hand to go clockwise, okay, I can't do that. My fingers don't bend that way. So what I'm going to have to do is something really cool that humans can do, right? I'm just going to turn my hand over, right? And now I can bend my fingers and I'm going to get a north down. So what we say in physics or in physical science is that when one electron is spinning this way, it's going to create a north down, and when the other one is spinning this way, it's going to create a north up. And so we're going to end up with these two electrons spinning, and they're going to be creating opposite polarities or opposite poles of magnetic charge, which is good because that's going to allow them to stay together in the same orbital. So we say that one electron goes spin up and one electron goes spin down, and how this affects you and your drawing of the electron configuration is that that's going to give us an arrow up or an arrow down to represent the two electrons that are in each of these 5d3 sublevels. Okay, and so this moment, this overall picture of our quantum numbers, they give us an address of where the electron is. It's 2 orbitals away from the nucleus, it's in this shape, it's along this axis, and it is spinning in this direction. Okay, so we get this kind of address, just like we know that you are in Torrance and you are on Torrance Boulevard and you're at 5430 and you're in room 103. It's giving us a more and more accurate location for where the electron is inside of the atom. Of course, keeping in mind Heisenberg uncertainty principle, we actually don't know where the electron is inside of the atom. Pretty fun, right?